the Hagener point. So what I was doing last time was to sort of develop some general machinery, a general approach to bound the size of a Selmer group. And I placed the discussion in a broader context. So I gave myself a finite module over the Galois group of K, any finite module M, and a collection of what I called Selmer conditions, which was the data for every prime V of K of a subgroup of the local cohomology group, H1KVM, with the restriction that for almost all V, this should be the set of unramified classes. And then we saw that we could define, associated with this data, a Selmer group, depending on L, which is the set of global classes which locally, at every place V, land in LV. And the goal now is to try to say something about the cardinality. We saw that this Selmer group is always finite. We would like to say something about its cardinality in a way. And so that's so I want to sort of complete first these kind of generalities. And now I want to say something about duality. So given any finite GK module, we can associate to it what's called its Kummer dual, which is it's closely related to the Pontryagin dual. I mean, it is the Pontryagin dual, but with a twist for the Galois action. So instead of so if you were taking the Pontryagin dual, you would take Homs into QP mod ZP, but here you take Homs into roots of unity. You take Hom of M with values in the multiplicative group, or GM, or what's the same thing, Hom of M. Since M is a finite module, in particular discrete, this is the same thing as the Homs of M into mu, mu cardinality of M, if you want. So this is the Pontryagin dual, but with a Galois twist. So the action of the Galois group, of course, takes into account the fact that the Galois acts in a certain way on the roots of unity. Okay. So so this is sometimes called the Kummer dual of the finite module M. Oh well. So if I have some G in M star, how does Galois act? Well, sigma acting on G is just what you would expect, namely sigma G, sigma inverse. Okay, so it's the usual conjugate. So if I want to define a left action. Okay. Okay. So we have a cup product from the H1, so the local H1, KV with values in M, and the H1 of KV with values in this Kummer dual. So of course, so this, I can map this to H2 of KV with values in M tensor M star, but now I use the fact that M star is M Hom M with values in root unity. So this is H2 KV with values in GM, which is an object which you, by now in the summer school, you know very well. I mean, you've seen many lectures on the Brouwer group in previous weeks. This is just the Brouwer group of KV, which is canonically identified with Q mod Z. So we have this canonical bilinear pairing, I mean, this, between these two local cohomology groups with values in Q mod Z. And this is something called the Tate pairing. So it was first studied, this duality was first studied systematically by Tate. And we have the following basic theorem about this pairing. So the general results on duality for local Galois cohomology. So this pairing, so I'm going to give a name to this pairing. I guess I'll call it like this with angle brackets sub V. Okay? So the pairing is a non-degenerate, so both on the left and on the right, non-degenerate bilinear pairing Okay, if the place V, the prime V is good, remember I introduced this also last time, it means that the module M is unramified and V does not divide the cardinality of M. So if V is good, then the unramified cohomology classes, the thing which I denoted by H1 finite KVM, and H1 finite KVM star are orthogonal complements of each other under this pairing, are orthogonal complements under this. So I mean that this set of unramified classes is the exact annihilator of this one under the Tate pairing. Okay? So that's sort of the basic result we'll be using about this Tate pairing, which was theorem due to Tate, which was written up. Well, you can find it in Milne's book, for example, on arithmetic duality theorems. So as a corollary of this theorem, you'll note that if LV is a set of Selmer conditions, for this Selmer group H1 KM, then I can also consider the orthogonal complement. So I can define LV star to be simply the orthogonal complement of LV under the Tate pairing. Okay, that's my definition of LV star. Then this is also a set of Selmer conditions, because LV for almost all V is the unramified classes, and then LV star will be also the unramified classes for the Kummer dual. So it's also a set of Selmer conditions, and that means that we can define a dual Selmer group. No, it needs to be the unramified. It needs to be H1 finite. That's my, right? If it were the entire group, then this Selmer group would be infinite. So you want the unramified classes. And the point is that when you take these orthogonal complements, you will still have unramified classes. Take an orthogonal complement of unramified classes, you get the unramified classes for the Kummer dual. So you have that, and then what that means, so that allows me to define the dual Selmer group attached to. So I mean, you have to be a little bit careful about the terminology, because the dual Selmer group is going to be a subgroup of the local Galois cohomology group. It's not at all dual to the original Selmer group in the sense of it's not a dual, but it's defined via duality at the local level. So the dual Selmer group, which I'll denote by H1 sub L star K M star. Well, so this is called the dual Selmer group. Yeah, so L star, it's a piece of notation. So L star is the collection of LV stars. Okay. And this is called the dual Selmer group. So the dual Selmer group of H1 Km. And the main result is that, so these Selmer groups, their cardinalities are very subtle. I mean, there's a whole industry in number theory right now which tries to control the cardinalities of these Selmer groups and relate them to special values of L functions and so on. But although the orders of Selmer groups are kind of subtle and hard to understand on their own, the point is that the cardinality of a Selmer group and its dual Selmer group are related by a simple formula. And that's going to be the key to, yeah.
So your definition, in places where LV is the whole, you have a complete description of the LV star in those cases.
Yeah.
Meaningful. Is there such a thing for a bad place?
For the bad places, no. I mean, it is what it is. It's a little bit harder to control. I mean, also, this theorem of Tate can be made quite explicit for the good primes. It's considerably more involved at the bad primes. So here I'm taking this a little bit as a black box, this duality, the fact that you have it for all the places, and that therefore having chosen some local condition at V, you have a dual condition. Okay? And you need this kind of precise understanding of the local duality, also the bad places, to really be able to write down the statement to prove the statement I'm going to write down now, which is a kind of, so this theorem, this is an important result. I mean, it really uses the full machinery of global class field theory for proving this. It's a kind of, you'll see it's a kind of Riemann-Roch theorem. So it has a flavor, anyway, of a Riemann-Roch for Selmer groups. In the form I'm going to state it now, it appears in a paper of Greenberg, Ralph Greenberg. I mean, although, yeah, and the formula is the following: that if you try to, so if you look at the order, the cardinality of H1 sub L Km, so the Selmer group attached to the choice of these local conditions, and you want to compare that with the cardinality of the dual Selmer group, H1L star Km star, you can write this ratio as a product of simple local terms, which are easy to control. So, well, you have a ratio of H zeros, or global H zeros, H0 Km, divided by the cardinality of H0 Km star. That's not very difficult to control. I mean, in fact, very often, certainly in the context at hand, these M's that we're dealing with elliptic curves will have no H zeros. So anyway, H zeros are always easy to compute. And then we have a product of local terms. So the cardinality of LV divided by the cardinality of H0 KVM. So the invariance of M under the action of KV. Maybe this is a good point to, okay, so this is the formula. Okay? Now, maybe let me make this as a remark that if V is good, then the cardinality of H1 KVM finite is equal to what's downstairs, so the cardinality of H0 KVM. And I leave this to you as an exercise to think about. I mean, okay, there are various general results which would allow you to prove this, so you can actually just do it by hand. I mean, study the finite classes. I mean, you can really write it down. I mean, this is using the, yeah. Which H1 of M is a finite module. M is a finite module, so everything is finite, sort of. I mean, for the local Galois cohomology, even the full local cohomology is always finite. So the global H1 Km, could certainly be infinite. But I'm cutting down its size by imposing these local conditions. Once I put this L here, so this, I mean, it's by no means a trivial fact that this is finite. This is using here Hermite-Minkowski, okay? But I claim that the fact that these, I mean, okay, I mean, it's not enough. I mean, okay, these terms are all finite, I'm claiming, okay? But you need more than that because you're taking a product over all V, right? So you need to know that these terms are 1 for almost all V. And what I'm saying is that if V is good, then the finite classes are equal to this H0. And by my definition of Selmer conditions, these LVs are H1 finite for almost all V. So almost all terms in this product are 1. Okay? So that's certainly something that you need to What is it? Absolutely, absolutely, yes. Because for the final, yeah. Okay, so you're doing the exercise, yeah. So that's a. Yes, yes. I mean, you could rewrite this by sort of interchanging M and M star, and yeah, you will get.
But then you're saying that for be good, LB star equals the whole thing for the dual. So how can it be?
I mean, if you
Confused about the linear algebra.
it should work out. I mean, if you look at this formula, right? It's true that there's symmetric under M and interchanging M and M star and L and L star, right? So if you write, but on the other hand, the right-hand side is not. It doesn't appear to be symmetric under this interchange, but you have to work it out. I mean, believe me, it works. It's not. Okay, so there's also an exercise. I mean, convince yourself that if you write down this formula for M and M star interchange and L and L star interchange, you're not going to get anything new. You will get an expression which looks different on the right, but is really the same, and it's an exercise to show that those two things are the same. Okay, and okay, maybe this is one exercise. Maybe another exercise which I'd encourage you to think about, since the theme of this summer school is really algebraic geometry. I mean, so those of you who are more geometers at heart, I mean, try to understand or think about the analogy between this formula and Riemann-Roch, and maybe try to turn it into more than a vague analogy, but make it precise. And so try to flesh out the analogy with Riemann-Roch for this formula. But this is kind of an open-ended exercise, of course. There's not one solution. I mean, okay. So the key special case for us, of course, is the one that I mentioned at the end of my last lecture. So the important special case is the one where M is the module of p division points on E. And then we note that the Kummer dual of this module is canonically identified with EP thanks to the Weil pairing. Okay, so the Weil pairing is a pairing on EP cross EP with values in mu p. So EP is identified via this pairing with the harms of EP into mu p, into the roots of unity. So the EP is canonically its own Kummer dual. And then we have a lemma that says that the Selmer group, the P Selmer group of E over K, so the one which you get by taking for LV the image under delta V of E of KV mod P, this Selmer group is equal to its dual, is equal to its dual. In other words, what I'm saying here is that these LVs are their own orthogonal complements relative to the Tate pairing, to the local Tate pairing. And this is kind of notable because you see these LVs, they depend on the elliptic curve. I mean, I could change the elliptic curve, maybe have the same EP, but maybe, for example, if I have bad reduction, I mean, I still have this statement, this local statement that the image of the local kinetic homomorphism is a sort of a maximal isotropic and is its own orthogonal complement under the Tate pairing. Okay, so knowing that the P Selmer group of E over K is equal to its dual, if you plug it into this formula, then of course on the left you're going to get 1, right? The order of the Selmer group divided by the order of the Selmer group. So what you find then is that 1 is equal to whatever it had to be. In this case, it's going to be the product over all places V. So I mean, these H0 terms in the context where I'm placing myself are 1. But anyway, certainly the ratio is always 1. But in any case, I'm assuming that M has no stable subspaces. So here I'm taking, I'm taking K equals Q, I guess. But okay, what I'm saying here is true for general K. So might as well stay on that level. So it's E of KV mod PE of KV divided by EP of KV. Okay, that's what I get as the product of local terms on the right, right? Because because LV is just this. It's the image of this under the corner. So that's the cardinality of LV up here. And the H0s of KVM are just the points of order P defined over KV.
You're assuming P is not 2.
Am I assuming that P is not 2? Oh, because you're worried about the complex places, about the infinite place. You see, this one is true regardless of M. It's also true if M is of order 2, but you're right. You have to take a product over all places. That's important. In fact, it's always important. It's good that you point out. I take over all places, including the Archimedean places. Otherwise, it's not true. And then having said that, I guess, okay, yeah, I mean, let's assume P is not equal to 2. Otherwise, you get an extra contribution here. It doesn't, yeah. Yeah, I mean, I assumed from the outset that P is not 2. There would be many other problems that will surface later if P equals 2. In Kolyvagin's method, you're going to see we're going to use eigenspaces under various involutions, and then it's better to be with an odd prime. Okay, so we get this formula. And okay, so I want to. Yeah, okay, maybe this also you want to think about to try to prove this. So, exercise actually. Prove this directly. I mean, this is also a fun exercise. Prove this directly. And okay, I mean, if you do this, you'll see that the interesting part of this exercise is that these individual terms are not all one. Okay, so you really need that. What happens is that you're going to have two V's that are going to contribute something special. So do this directly for K equals Q. Okay, let's just think about the case K equals Q. You're going to have two interesting places which are going to contribute something, namely V equals P and V equals infinity. I think that for V equals infinity, you're going to get a 1 over P, and for V equals P, you're going to get a P. So, but then these contributions cancel out, that infinity and P. For all the other V's, this term is going to be 1. But so it's a local calculation, so you can do it directly. You don't need this global result, but out of the local calculation, you can at least conclude that the cardinality of the Selmer group and its dual are equal. I'm telling you that something more is true, that in fact the two Selmer groups are really the same. Okay, so now I'm going to fix S to be a set of good primes, a set of primes which is good for, so L, set of primes L not dividing P times N in this case. N is the conductor of the elliptic curve, and P is the prime, the descent prime which I chose, right? So L not divides Pn for L and S. Okay, so I want to now define two new Selmer groups. So one of the ideas in the method is to try to study the Selmer group of E by changing the Selmer group by allowing ourselves to vary the set of local conditions which we impose on the cohomology classes. So I'm going to define two types of Selmer group, the relaxed Selmer group at S, the relaxed Selmer group is going to be denoted in the following way. I'm going to write it cell PE over K with a round bracket S here. So this is just the set of classes in the Selmer group in H1, in the global cohomology, H1 of KEP, such that the restriction at V of this global class belongs to delta of E of KV mod P. But I'm going to insist on this condition only for the primes V which do not belong to S. So at the primes in S, these classes can be whatever they want. Okay? So this is sort of relaxing the local condition. I don't insist anymore on being a local point at S, but you can be whatever you want. So this is sort of a potentially larger Selmer group than the original one. And then you can also consider the restricted Selmer group, which is what you get by insisting that the classes are 0 at S. So this one I'll denote by cell P of E over K with a square bracket S underneath. So this is the set of classes C in the Selmer group. So I insist on the Selmer condition everywhere. But I, in fact, insist on more. I want that the restriction at V of this class should be 0 for all V in S. Okay? So you have these two flavors of Selmer group, one where you relax the local conditions at S, and the other where you restrict the local conditions, that you require that the class be 0 locally at all the primes dividing S. Sorry, in my relaxed here? Is that what you're asking? H1, yeah, so this is just, yeah, P torsion again. Sorry. Sometimes I write, I mean them, yeah. Okay. So an easy lemma, is that these Selmer groups are dual to each other. Okay, the restricted and the relaxed, the P Selmer group of E over K, relaxed at S, is dual to the relaxed, I mean to the restricted Selmer group. I mean, that's clear to see because what's dual to allowing, I mean, the orthogonal complement of 0 is the H1 KV, right? Yeah. No, it's still a Selmer group. Oh my God, I'm sorry. No, but you see, I'm asking that the restriction at V of C belongs to this for all V not in S. So I'm only changing the Selmer conditions at a finite set of primes. Before I was insisting that for the V in S I should land in here. Now I don't insist on anything anymore.
So S is finite?
S is finite, I'm sorry. Yes, S is a finite set of primes, of course. Is that what's bothering you? S is a finite set of primes. No. I mean, well, I mean, the way I wrote it, it could be anything, right? But I mean, I really want it to be a finite set of primes.
So it's not a set of all good.
Set of good, oh yeah, no. I went A set, but more than that, I want A finite set, yes. Okay, yeah, sorry, I didn't, yeah, definitely.
Another question. Instead of dual, don't you want orthogonal too? Because as you increase S, one gets bigger, the other gets larger. You can't stay dual to each other.
Exactly.
So you don't want dual on the road, you want orthogonal.
No, but when I say this is dual, I don't mean that these are in duality, right? I mean, is V dual? I mean, okay, this is I warned you before. This is a confusing terminology. I mean, is V dual Selmer group of, it's the dual Selmer group. All I'm saying is that at the level of the local conditions, the orthogonal complement of 0 is H1 KV. Yeah, that's all. Of course, they're not in duality. I mean, their cardinalities are going to be different. Okay. Of course, I mean, this one you're making it larger, this one you're making it smaller. Okay. Okay. So, but now you see, we can apply the theorem, this kind of Riemann-Roch for Selmer groups, to this situation, right? And you find that the cardinality of the P Selmer group of E over K relaxed at S divided by the cardinality of the P Selmer group of E over K restricted at S. Well, what are you doing here? You're just changing these local terms on the right at the primes dividing S. At the places dividing S, you've enlarged LV, you've made LV bigger, and you've made it actually equal to the full H1 KV EP. And at the, okay, and that's it. I mean, here you still have the same H0 coming up, so which is the cardinality of E of EP of KV. But then you can also rewrite this, noting that the P torsion in E of KV is the same thing as the P cotorsion, because V does not divide P. So this E of KV is essentially, it's an extension of a finite group by a v-adic Lie group. So from the purposes of looking at P torsion and cotorsion and so on, it behaves like a finite group. So I can replace this by the product over V naught in S of the cardinality of H1 kV E square bracket P divided by E of kV modulo PE of kV. This is because V does not divide P. And then I can note that this is nothing else than the cardinality of the singular part of the cohomology, right? Because this is, the cardinality of this is equal to the cardinality of the H1 finite, and so this local H1 modulo of the H1 finite is just the H1 singular. So this is equal to the product over V and S of the cardinalities of the singular parts of the cohomology of KV EP. So I have this important kind of a useful numerical equality, so I know that the order of this relaxed divided by the restricted is the product of the singular things at the places. So now I'm going to try to exploit this formula by giving myself a particularly good choice of choice of finite set of primes S. I'm going to say that a set S controls the Selmer group, controls the P Selmer group of E over K if the restricted Selmer group at S is 0. In other words, what I want is that if I look at the natural map from the P Selmer group of E over K to the direct sum over V and S of the finite parts, if you want, of the cohomology with values in EP, that this should be injective. In other words, I capture my global classes from their local behavior at S. Like they're completely determined by local behavior at S. Now, it's not unreasonable to think that you would have such sets that control the Selmer group, since we're starting with a finite set of cohomology classes. And so it's reasonable to think that you might be able to cook up such a set, and we'll see shortly that you can do that using sort of Chebotarev type arguments. Okay. It's true, right? No, it's not completely true. I think it's not completely true. There are cases. I mean, well, no. I mean, in the case with my E, right, with the assumptions I made on EP, and so it's certainly true, and I'll be explaining a little bit why that's true. It's basically Chebotarev, right? But you have to be a little bit careful when you work with modules with non-trivial Galois action. So I think there are some examples. Some people might know this actually in the room. There are examples where this can never be made to. Because when you want to control this via Chebotarev, you first make a finite extension where the module becomes trivial, and then you can apply Chebotarev. Yes, I mean, so for a general M, I don't think it's always true that you can find a controlling set.
Well, if it is unoccupied outside the finite set of prime, you can always do this. I mean, Mason will get into that in their group.
So for any M whatsoever, there's no kind of pathological example where you...
Well, they have some hypothesis.
Exactly. People always make hypotheses that kind of... I think if you're kind of really... I wouldn't... Okay, maybe I'm not right, but I think it's... I think you need some hypotheses. I mean, if you think about the proof, well, anyway. Okay. Yeah, I think that could happen, yeah. It's one of these, local, global things that... Yeah, in other words, right. I mean, you could have a class which is non-trivial, but locally trivial at all places. I think this can happen. It's a bit subtle because it's a discrete module still, but But I don't have a counterexample in mind, though. Okay. What did I want to say? Oh, I just remembered, actually. There was an exercise I wanted to give, which I forgot. Let me add it here, actually. Something that was suggested to me by Popescu. I don't know if he's in the room, but anyway. So the exercise is this. I should have done it earlier. So exercise. What does this Riemann-Roch for Selmer groups say? What does it tell you when the module M is Z mod PZ? So the cyclic group of order P with trivial Galois action. So that M star is equal to mu P. So when you kind of specialize this duality result, which I wrote down, to this case, you should recover a familiar statement of class field theory. Of course, this is not a proof of that because the proof of this duality theorem, it uses all the full machinery of class field theory, but you can see that. So, I leave that to you to think about. Sort of make everything explicit in that case. It's well worth doing. These Selmer groups have very classical interpretations in terms of class groups and units in this case, right? Okay. So now I'm going to suppose that I have a set of primes which controls the P-Selmer group. And then I observe two things, okay? The first thing that you can observe is that, well, like what I said before, the cardinality of the P-Selmer group of E over K relaxed at S. So you see this formula here relates, where's my formula? Here, right? I have this formula which relates the cardinality of the relaxed and the restricted. But in this case, if S controls the Selmer group, the restricted Selmer group is 0. This term goes away. And then I have a formula for this one. It's just the product of the H1 singulars. So the relaxed Selmer group, its cardinality is equal to the product over the V dividing V and S of the H1 singular K, V, E, P. That's the first thing. The second thing is that you have the obvious exact sequence, which goes so you have the obvious map from the P-Selmer group of E over K, relaxed at S, to the product over all V of the H1 singular, V and S, sorry, of H1 singular KV EP. This is just a natural restriction map. So okay? But now, you see, so you have these two groups. They have the same cardinality by what I wrote in A, using this duality, and you have a natural map from one to the other. But this map is, of course, not an isomorphism. It has a kernel. If you take a class and you relax at S, what does it mean that this class has a trivial singular part at all the V and S? It means that it's a Selmer class. It belongs to the Selmer group. So the kernel of this is the P-Selmer group of E over K. So you have this exact sequence. But these two groups have the same cardinality. And you're trying to understand the kernel of this map. So this is just the residue map, right? Or I'll call it D. It's really the sum for all the V and S of the residue at V. So to control the kernel of this map is the same thing as controlling its co-kernel, because these have the same cardinality for this set of primes which controls the Selmer group. And therefore, the problem becomes transformed into one of trying to manufacture enough cohomology classes in this group whose residues you can control, so that you kind of get a big image here. If you can show that this co-kernel has order at most something, then you've bounded the Selmer group. So the problem now becomes one of bounding the co-kernel of this map D, this residue map. And so then now your problem is turned into one of construction. You need to manufacture ramified cohomology classes. So there's this sort of philosophy that when you want to understand the unramified classes in a Selmer group, it's enough to be able to control the ramified classes, and then you have control over the. This is certainly, I mean, I think it's a principle which underlies any of these recent works, Kolyvagin's firstly, and the later works of Wiles for the Selmer group of the adjoint, always rely on this basic principle that they turn it into a problem of construction, of constructing ramified classes and controlling their residues. Okay, so that's all I wanted to say about the formal aspects of the argument, okay? That's sort of the general strategy for bounding a Selmer group, but now we have to put something into the machine. I mean, we need to actually construct these classes, right? And we're going to do that, and for that, there is no general recipe. There's no general method. It's very much it's much more of an art than a science, and I'm going to explain to you how it's done by Kolyvagin in the case of an elliptic curve over the rationals, and the way it's done, how these classes are constructed, these ramified classes are constructed using Heegner points. So you need this this structure to be able to manufacture these classes. Okay. So maybe before I go on, maybe this is a good point to pause and ask if there are questions. So now I'll be going to, so this is sort of the second part of my talk. I'm going to talk about Kolyvagin cohomology classes. Kolyvagin classes. And so now I'm going to revert. So from this great generality, I'm going to go down to the case that I'm really interested in, okay? So my M now, my module M is just the is EP, but moreover K is, what is K? So K is going to be my quadratic imaginary field, which I had in the statement of Kolyvagin's theorem, okay? Imaginary field. And E is an elliptic curve defined over the rationals, okay? So it's equipped with, this EP is equipped also with an action of a GQ, although for most of the argument I'll view it only as a module over the Galois group of K. But at some point I'll also be using the fact that it's defined over Q. So that's sort of the special setting in which I am. Okay, so now I want to kind of identify some good primes that I'm going to put in my set S. And those are going to be called Kolyvagin primes. So this is a definition. These are primes that Kolyvagin uses. A prime L, for the purpose of this argument, is called a Kolyvagin prime. No, of course not. In fact, yeah, it became a standard terminology later, I guess. The Kolyvagin prime relative to the pair, or the triple consisting of the elliptic curve, the quadratic field K, and the prime P, so it depends on this data, if the following conditions are satisfied. So the first condition is that L does not divide 2 times the conductor of the curve times the discriminant of the field times the prime P. So you try to kind of make it be relatively prime to all the everything in sight somehow. And you also want that L is inert in the quadratic field K. That's the first series condition. You're throwing out half the rational primes by making this condition. The second condition is that the prime P should divide, I don't know why I said exactly. P should divide the Lth Fourier coefficient of the modular form F, or the AL of E. Okay, I remind you that AL of E is just L plus 1 minus the cardinality of E over Z mod L. The third condition is that we want P to divide L plus 1. So you have various congruence conditions on L and AL modulo P. And, okay, so these are the conditions. And sort of a lemma, which is important actually, is that, okay, I mean, these are not 2 restrictive conditions. There are, in fact, infinitely many Kolyvagin primes. And the idea is that it's a Chebotarev argument. I mean, these 3 conditions can be rephrased. So L is a Kolyvagin prime if and only if the Frobenius element, so if I look at the Frobenius element at L, in the field which you obtain from K by adjoining the coordinates of the p torsion points, the Frobenius over Q, is equal to the conjugacy class of complex conjugation. I mean, remember that the conjugacy class of complex conjugation is acts on the p torsion with eigenvalues 1 and -1. And so the trace is 0, the determinant is -1. And on the other hand, the trace is AL and the determinant is L. So you can sort of, I let you work this out. This is an exercise to show that you can rephrase this as a condition on the Frobenius element at L in a certain finite extension of the rationals. And therefore, you have infinitely many Kolyvagin primes. Okay? So maybe so L is a Kolyvagin prime if and only if this is true. Okay, complex conjugation is non-trivial in Gal K over Q, and that means that L is inert. And so you can see that. So okay, that tells me that I have at least a reasonable machine in Riemann-Roch theorem for producing many Kolyvagin primes. And in fact, I want a bit more than that. I want to be able to say that I can control the Selmer group by Kolyvagin primes. That'll come up later a little bit. Okay, so we'll see later that not only do you have infinitely many, but in fact, you have enough Kolyvagin primes to be able to control the Selmer group. But before I do that, let me now describe the construction of certain cohomology classes, which I'll call kappa of L. And so these are going to be cohomology classes which I construct from Heegner points. So these are the famous the famous cohomology classes that Kolyvagin constructs. So let me denote by n sub L the cardinality of the Galois group of H sub L over H, okay? Where I remind you that H sub L is the ring class field of conductor L, and H is the Hilbert class field. Okay, maybe I'll call this group also GL or something. Now, if you do a calculation from class field theory, you'll see that the cardinality of GL is equal to L plus 1 divided by some W, which divides 6. Okay, so this, you might have some W there. But essentially, the cardinality of GL is L plus 1. And in particular, this group has order divisible by P. P is my prime, my descent prime, which is bigger than 2. Okay. So now we consider, and I should say that this GL is also a cyclic group. So by classical theory, you can also see that GL is cyclic. And I'm going to write it as generated by some element, which I'll call sigma L. So sigma L is going to be a generator of this global Galois group, the Galois group of HL over H. So now I define an operator, following Kolyvagin. I define an operator in the group ring of this Galois group by taking the sum for j equals 0 to n sub L minus 1 of j times sigma L to the j. So this belongs to Z of GL, okay? And it's sometimes called the Kolyvagin derivative. I mean, if you kind of took the norm element, which you can write as sum of sigma L to the j, and you kind of differentiated it formally, you would get something like this, right? So it's a kind of... Okay. Okay, and I'm also going to need another element. I'm going to have to, in various points in the construction, trace everything down from H to K. So I'm going to introduce the trace operator to take the sum for all sigma in the Galois group of H over K of sigma. So it's like a norm element or a trace element for this Galois group. Okay, and I observe, so the key thing I'm going to use about this DL is that if you apply sigma L minus 1 times dl, you get the following thing. You get, let's see, what do you get? You get NL minus minus n sub L, where n sub L is just the norm. Okay, so NL here is going to be the sum of sigma L to the j for j going from 0 to NL minus 1. Okay, so I have this one, which is just the usual norm or trace, and this is sort of this derivative. And the point is that if you take sigma L minus 1 of this operator in the integral group ring, you get this, the order of the group, this integer, minus the norm. Minus the norm. Okay, this is a useful thing, which will be. Okay, so now I'm going to define my class by just taking the Heegner point of conductor L, which I remind you I called P sub L. So recall that we have the Heegner point defined over the ring class field of conductor L, which we called P sub L. So this belongs to E of the ring class field of conductor L. And now I'm going to consider a new point, which, well, here in my notes I call Q sub L. So by applying to this point these operators in the group ring, so I'm going to just take dl of PL, and then I'm going to apply N1. Sort of this is just to trace things from H down to K. Okay? So this belongs still to E of HL. Okay? I've just taken certain linear combinations of Galois translates of this basic point P sub L. But now the claim, the crucial claim, is that this point, although it lives over HL, if you work mod P, if you're just in this point modulo P's powers, it somehow descends. It wants to descend. It's invariant mod P. So the claim is that QL, this point, belongs, so if I look at its image in E of HL modulo PE of HL, it actually lands in the Galois invariance of this. So the points, the elements which are invariant under the Galois group of HL over K. And the proof of this exploits the conditions that I had in the definition of a Kolyvagin prime. So yeah, I don't know if I said this, but anyway, I certainly should say this. This is only when, I mean, I can make this construction in any case, but I'm going to be interested in it in the case where L is a Kolyvagin prime. Okay? So I claim that this is true. Why is that? Well, okay. So let me first show that this is invariant under the Galois group of HL over H. The Galois group of HL over H. So I take sigma L, this is the generator of this Galois group, minus 1, and I apply it to this point Q sub L. So what happens when I do that? Well, this is just sigma L minus 1 times dl times n1 evaluated on the point PL. But by this formula, which I wrote here, this is just NL minus the norm sub L evaluated on N1 P sub L. But now you'll note that P divides NL. NL is the cardinality of this group, so it's essentially L plus 1, and our assumption on Kolyvagin prime was that P divides L plus 1. So this is divisible by P. And yeah, so this is congruent modulo P's powers of points to minus N1 NL P sub L. But what is NL of P sub L? We saw last time when we discussed the norm compatibilities of these Heegner points that if you trace the Heegner point down to the Hilbert class field, you get AL times P1 because L is inert in K. But this is also equal to minus N1 times AL of the Heegner point of level 1 in the Hilbert class field. But this is certainly congruent to 0 mod P. Because P divides AL, that was the other condition in the definition of a Kolyvagin prime. Okay? So now, and then for the other elements of the Galois group, it's even easier because you have this N1. So, well, I mean, it's not. This is the main part of the calculation, really, showing that this invariant under this Galois group of HL over H. But now I'm going to sort of, I guess I'll finish off by giving you a definition of these classes, and I guess in my next lecture I'll show you how they're kind of used to control the Selmer group. So I'm going to now define a class which I call kappa of L 0 bar. Okay? So this is going to be a class in H1 of the Galois group of GK, of the full GK, with values in E of HL. It's actually going to be the P torsion of this. So how do I define this class? Well, I'm going to define it in the following way. I say that kappa of L 0 bar, evaluated on an element sigma in the Galois group, is just the following thing. I take sigma minus 1 of this point QL. Now, I showed here that this QL is invariant mod P. So this belongs to PE of HL. But E of HL has no P torsion. So I can divide this by P uniquely. So this is an element of E of HL. And maybe I need to kind of give you an exercise to prove that in order to show that this is uniquely divisible, you need to know that E of HL has no P torsion. Okay? And I'll give you a hint to that for that exercise. I mean, it could be any sigma in GK. You see, in this claim, I'm saying that it's invariant under all of the Galois group of HL, okay, therefore of all of K. So I do this. So this is my formula for kappa of L0. Yes. So that's where you can use that in that exercise. For my P, yeah, but I mean, I'm maintaining all my running hypotheses. Okay, so the statement of Kolyvagin's theorem for P, I put that in the P, yeah, definitely. So, yeah, you want to use that here. So the elliptic curve can have a point of order P over any solvable extension, actually, thanks to this. Okay, so that's my kappa of L0, and now I just look at, I define kappa bar of L to be the element of H1 KE, which maps to this one. So, okay, so which maps to this one under, so let's be the corresponding class, okay? So I just compose of the inclusion of E of HL into E of K bar. And then, finally, I let kappa of L, my class that I want, be any lift of this kappa of L bar to H1 of K EP. So remember the fundamental exact sequence which I'm using here is the one which goes from H1 of K EP to KE P torsion, and with kernel E of K mod P, E of K. So I've constructed a class in here, a P torsion class. I mean, it's not hard to show that this class is killed by multiplication by P. Okay, just look at the definition. And I just take this class and I lift it to here. And that's my kappa of L. Okay? And, okay, so maybe it's good to end here. I mean, I'll end with the construction of these classes. And in the first maybe half of my lecture next time, I'll explain quickly how these classes, what are their basic properties, and how these basic properties can be used to actually, what we're going to show really is that we can, and now the strategy is clear, right? We have this machine for manufacturing cohomology classes in terms of Heegner points. We're going to show that these cohomology classes can be used to control to produce enough ramified classes so that the co-kernel of this map residue is of dimension at most 1. That's going to be the argument. So that's it for today. So actually, before I end, I just want to make a last comment, which concerns the lecture of this afternoon by John Voigt, which is going to be about Shimura curves. And this is sort of taking up a theme that I want to discuss more tomorrow and on Friday, which is the problem that this proof of Kolyvagin's theorem that I'm describing here, this whole strategy for understanding BSD, is very much tied to the rational numbers. Okay? So it seems like, because we're using the fact that elliptic curves are modular, so that for any elliptic curve over Q, you have this nice parametrization by a modular curve. So one thing we'd like to do, especially if you're interested in this kind of from a kind of Diophantine point of view, understanding sort of the general theory of curves, you would like to have similar evidence for the BSD conjecture for elliptic curves or abelian varieties over general number fields. So you might ask whether there are similar parametrizations and CM points in other contexts. So what John is going to explain this afternoon is that there are generalizations for certain number fields which are called Shimura curves. I mean, these Shimura curves were already alluded to in a number of other lectures previously. For example, in the lecture of Noam Elki's, these were mentioned briefly. And so these actually work in the context where we have an elliptic curve defined over F, which is a totally real field. And then a lot of Kolyvagin's general strategy, I mean, these Shimura curves are also equipped. We can find our elliptic curve in the Jacobian of these Shimura curves in many cases. The Shimura curves are with a nice collection of CM points. So we can kind of run through this whole Kolyvagin strategy and Gross-Legge strategy in this context as well. So we have a lot of evidence for BSD also over these totally real fields thanks to these new kind of curves. And I'll be talking about them more. I mean, so John will talk about them this afternoon from a computational point of view. So